Hello, this is Sharon Fisher from Teledyne ISCO, and today we are very fortunate to be joined by Tracom. They are going to help us present on fundamentals of flumes and flow. From Tracom, Andrew Helbling is with us, who is their sales and engineering manager. And from ISCO Water, we have Darrell Kuta, who is one of our regional managers. So with that, I will turn it over to Darrell.
Well, thank you for joining us today. I am delighted to be joined today by Flume expert Andrew Helbling from Tracom. And as Sharon mentioned, I am Darrell Kuta with Teledyne ISCO. We will discuss the fundamentals of flumes and flow rate calculations. Andrew will enlighten us on primary devices, also known as flumes, and I will discuss secondary devices known as the sensors and flow meters. Today's agenda: we'll discuss the fundamentals of flumes, applications, flume designs, and I will discuss the level measurement options, flow calculations, and how to receive the data after it's been calculated through the flow meters. So with that, I'm going to turn this over to Andrew, so he will discuss the flumes or primary devices, and I will follow it up with the secondary devices. Thank you.
All right, thanks for the introduction, Sharon and Darrell. I'm happy to be here. Today we're going to be talking about flumes, the fundamentals, basic designs, their applications, and some design principles. With that, we'll go ahead and get started. So we'll start with the basic definition. A flume is a static hydraulic structure that moves water or another effluent through it and accelerates it. And with that, it moves from typically subcritical to critical flow, and that creates a standing head upstream that can be measured. They're pretty standardized depending on the type. There are some proprietary, but the majority of them are public domain. They're developed by the government. They're paired really well with a lot of different electronic sensors that can report that data back to a central unit. So whether it's an ultrasonic meter or a bubble tube or a radar, they all provide a good standardized head-to-flow conversion point and a good sample point to take other draws from. Some good applications, we see them in a lot of different industries. So agriculture, the partial flume and trapezoidal flumes were developed specifically for water rights management out west. We see environmental monitoring, so dam seepage, looking at small streams and headwaters, looking at how those affect larger tributaries. And of course, the biggest industry theme is municipal wastewater and industrial wastewater and water resource management. So like I said earlier, they are hydraulic structures. They move water or other effluent through from a subcritical to critical flow. And you can see in this picture on the left here is a large partial flume. You can see that there's a level difference from the bottom closer to the screen and then to the higher part, and that's a good implication of how that will work. We have a lot of different types that we see: partial flumes, palmar boluses, trapezoidals, cutthroats, and H flumes. They're all designed for different flow conditions and accuracy. Each one has kind of like a different niche it's settled itself into. So partials are a good all-around flume. Palmar boluses you mainly see in water and wastewater and sewer. In H flumes, you see a lot more in agriculture and some mining applications as well. So some best practices for designing your application. You got to start with the influent, the flow coming into the flume. If you don't have that settled in, then you're going to be not off to the races. So the number one thing you need to look at is it needs to be subcritical, the flow coming in. If it's already moving too fast, then the flume will not be able to accelerate the water, and you're not going to be able to get your standing head the way it needs to be. And it also needs to be tranquil and uniformly distributed, or laminar. So we typically do this by having a good straight flat inlet proper wing wall use or the use of an integral approach section. For the majority of flumes, so your partials, your trapezoidals, and even some palmar boluses, we kind of have a general guideline. You want 10 to 20 times your throat diameter straight flat upstream. And that will give you typically subcritical, tranquil, and uniformly distributed flow going into it. When installing the flume, it's imperative that it's level front to back and side to side, unless it's specifically prescribed to be at a little bit of an angle. That works for palmar bolus flumes, and some trapezoidal flumes can be set at angles, but it's important to note that when they're at that angle, the level needs to be adjusted, so it actually raises the level up a little bit. So there's a little bit of a difference from what the staff gauge would read to what it should be. And when using measurement devices such as a bubble tube or an ultrasonic, they need to be set at the exact point of measurement. This is often found on the shop drawings, or as you can see in this picture, it's just directly across from the staff gauge that was installed at the factory. On the effluent end, it's important to have your flow be free flowing. Some flumes can be submerged, which is where the measurement downstream is compared to what it is in the converging section. And you can do a conversion factor on that to find that area. Flumes like Montana flumes are designed to never be submerged. If they are submerged, you'll automatically just lose all of your accuracy. So it's important to, when designing, just go ahead and design for free flow conditions. That way you avoid any of those downfalls of submerged flow. So when selecting a flume, there's a few simple questions I like to ask a customer, or if you're designing, asking yourself. Number one, what are the flows? Obviously, if it's a flow measurement device, you need to be able to size it appropriately and know which type you're going to look at. So you need to know your minimum flow, your average flow, and an instantaneous max. It's best to look at this value in gallons per minute. More macro units, such as million gallons a day, you can lose values and instantaneous maxes, especially if it's an industrial process where you're going to have batch discharge. You can have a really high batch discharge that will be, say, 200 gallons per minute, but overall you're going to have a really low gallons per million gallons per day. So look at it in that nice small unit, gallons per minute. That gives you a much better view of what we're actually looking at. So as a quick example, say we're working with a customer, I'm going to have a minimum of 20 gallons per minute, a max of 120, and an average of 60. We'll kind of move through these example by example, and then we'll kind of prescribe at the end. The next thing is going to be, is there going to be debris or solids? Some flumes, like small partials, 1 and 2 inch H flumes, and some trapezoidal flumes, 60-degree at low flows, that can get clogged really easily because that is such a tight throat. Some have ramps that can cause sedimentation, like an RBC flume or a palmar bolus. So it's important to know whether or not you're going to be able to pass your effluent through the throat. So in this example, we're going to have some sanitary solids, rags, and other things in the flow. And then lastly, we need to know if the flow is going to be in a channel or when it's piped. Flumes that were originally designed for channelized flow, like a partial or a trapezoidal, have had end adapters developed for it that you can allow pipe flow. Others, like palmar bolus flumes, were originally designed for that pipe or a circular channel. So it's important to know how we're going to be inserting the flume into the flow. So in this example, we have a 6-inch PVC running through either a manhole or just open in a plant. So if we put all this together, we have a 6-inch line with some sanitary solids and this flow. That's going to be perfect for a 6-inch palmar bolus, which is exactly what it was designed for in the first place. You could also use a 3-inch partial. That would give you a much larger possible max, running the 800s rather than 120. So if you're in a development that's going to be expanding, say you're going to have more houses, you're going to be expanding your brewery or something, maybe it's smarter to go with a larger flume. That way you have room to expand into. Unless we're going to do a quick little comparison of flumes. So partial flumes have a pretty big flow rate. So They're good for situations where you're going to have a wide range of flows, but the issue with them is when you have a low head, so anything say under a specific amount that's for the size, it's not going to measure well. So low flows, it's not really good for. Palmer boluses are the same. The flumes that you're going to look for really low flows are going to be your trapezoidal, typically a 60-degree V or an H flume. Those allow you to get down into about 1 gallon per minute or even tenths of a gallon per minute, as opposed to some of these other ones, which are good for, depending on the size, a more broad range of flows. Tolerance for solids. Partial flumes, like I said before, anything above a 2-inch throat is going to be really easy to pass things through. We don't recommend 1-inch or 2-inch partial flumes for sanitary flues or flumes that might have debris. Palm boluses are very tolerant. Trapezoidal flumes are tolerant only at high flows because they are V-shaped. At very low flows, some things might not be able to pass through that V-shape. H flumes are very intolerant at smaller sizes. Some of them only have a 16th size throat. So any sort of debris is going to clog that almost immediately. And cutthroat flumes are very tolerant. They don't really have a throat, they just have a pinch point, and all of them are very broad. And finally, some applications. We see partial flumes almost everywhere. They're probably the most ubiquitous flume. Most people, if you say flume, they're just going to think of partial flume. Palmer boluses, you're going to see in the wastewater industry, municipal and industrial. You mainly see them in pipe situations or maybe in a manhole channel that's still circular. Trapezoidal, you're going to see a lot of irrigation, industrial discharge. Same with H flumes, and then cutthroat flumes you're mainly going to see in the water and wastewater industry.
Well, thank you, Andrew. It was very informative information about the flumes and primary devices. So when ordering a flume, one thing to remember is just let your provider know what type of technology that you're going to use with it. If it's going to be a ultrasonic or a bubbler, which I'm going to show you those technologies in just a minute. But I will discuss the secondary devices used to read level and calculate flow. I will discuss the differences in the level sensors and list the pros and cons of each level device. And with that, we'll move on to the sensors. All right, so as far as secondary devices, there's 2 parts to it. You have the flow meter and the sensors. So what's the difference between the two? Both of these devices here are used with level sensors to calculate the flow, and they're both capable of having a modem installed so you can gather your data remotely. Now, the most common one that you're going to see with flumes is going to be our permanent meter. And so as far as the difference between a flow meter and a logger is a flow meter takes continuous readings. The readings are averaged over a period of time, say over 15 minutes. So they'll take continuous readings, average all those readings, and then log a 15-minute interval. They're usually AC powered, 120 or 240 volts. They can be powered by a solar panel. The nice thing is that they do have a local display. And as you can see on this one, it has a keypad, so you can do all your programming through the front, have your display showing your level and the flow rates to then calculate your flow. The other good thing about permanent meters is the outputs on them. Most flow meters will have either an analog output or Modbus output. That way you can send that data off to your SCADA system and inform the treatment plant of your flow rates coming in and out of your discharge. Now, portable devices are known as data loggers. And so what's different about that is they commonly run off of batteries. And so what they do is to conserve power, they take a snapshot of a reading. They wake up, take a snapshot, shut down for 15 minutes, wake up again, take another level reading, calculate your flow. And so the idea is that it's going to conserve power because it isn't taking readings all the time, and it just makes the assumption that the levels and flow rates were the same during that sleep time. And where you're commonly going to see this is at temporary temporary flow applications such as industrial pretreatment, or if you're just doing some spot checking. Now let's move on to the level sensors. So the different level sensors that are available are ultrasonic, which are non-contact. You have the bubbler, which is a wetted pressure transducer. You have the pressure transducers shown on the bottom, which could be either an area velocity sensor or an actual pressure sensors. Now keep in mind, these level measurement devices do not read direction. They just read level, and then we're going to use the flume to determine our flow rates. Now let's take a look first. One of the most common sensors that you're going to see is going to be the ultrasonic sensor. And as you can see here in the pictures, it's paired up with that flume. And so if you let the manufacturer, like Andrew, know what type of sensor you're going to use, they will supply it with the appropriate equipment to be able to install it at the right location. Now, the way an ultrasonic sensor works, you have a transducer, it transmits a sound wave, it bounces off the surface of the water, and it measures the amount of time it takes for that return echo to come back up to the sensor. And with that, it can determine the distance and the water level. Now, all ultrasonic sensors have a deadband because it takes a certain amount of time for it to be able to transmit and then receive. So you want to be careful when installing it that you make sure you have your sensor high enough above your flume or channel to properly read the flow rates. Now, the advantages of ultrasonic sensors, they're non-contact, which makes them easy to install. As we saw in that picture, it's mounted right on the side of the channel. They can be installed in the flume, or they can be supplied with a stilling well, where you can mount the sensor right over on the side of it. A non-contact sensor provides minimal maintenance. Because you're not in that flow stream, you're not worried about debris and other things getting caught on the sensor. Now, the disadvantage is the deadband that I'd mentioned, the beam angle. So as Andrew mentioned, sometimes you can get some narrow flumes. The beam angle of an ultrasonic sensor could potentially hit the side walls. And so that's why we have other technologies I'll mention here in a minute. Wind, steam, foam, those can also be issues for an ultrasonic because it'll have trouble transmitting that signal through the steam and foam, which you may find that at industrial applications. And last, turbulence. So if the flume is installed in the proper location, you shouldn't have turbulence here. But if sometimes you don't have enough room, it's mounted too close to a bend, you don't have the proper straight run, you may end up with turbulence, or there's debris in the bottom of that channel, which is creating your turbulence. Now, the other option is a bubbler level sensor. And so this is going to be used on the smaller channels. I find that a lot of these are used interchangeably between bubbler or ultrasonic. But the way a bubbler works is it measures the amount of pressure it takes to push out one bubble. And the bubbles come out at a rate of about 1 per second. And so and if there any debris were to cover the sensor, our equipment will send out what we call a super bubble. It builds up pressure, sends out 20 psi to self-clean that bubble line and give you continuous good level readings. So what are the advantages of a bubbler? Suitable for small channels. As you can see, it's just 1/8 of an inch line that goes in the bottom of that channel. It's not affected by the wind, steam, or foam, or even lightning because it's just a vinyl bubble line going into the bottom of the flow stream. So we have no electronics in the water. And only the bubble tube comes in contact with the flow stream. It provides accurate level readings. And as far as the bubble line going into the flume is inexpensive. So as far as maintenance, it makes it easy just to take that line out and clean it, or you can run compressed air through it to try to clean those lines. Now the disadvantage is, there's potential for a restricted bubble line because it is in the bottom of that channel. So if you have a lot of sediment going through there, there may be more maintenance required where you have to clean out the flume or use that super bubble to automatically clean it. Uses a little more power consumption because it does run a air pump to provide the air pressure, but a lot of the applications I find they're using AC power, so the power consumption isn't a big deal. This is a level-only device, so it does not read flow direction. Now, other options that can be used with Flumes are a differential pressure transducer. It's referenced atmosphere to atmosphere. It has a reference line from the transducer all the way up to the controller to reference atmosphere. Another good way to read level in your flume. The advantage of it, it's suitable for flumes. It isn't affected by the wind, steam, or foam because it's underneath the flow. They are highly accurate meters, but they do cost a little bit more because we have electronics in the flow stream. Some of the disadvantages you may find with a pressure transducer is sediment could cover it, power surge. If we had a lightning strike nearby, it can travel through the water and actually damage the electronics that are in the flow stream. And the other disadvantage is it does not read the direction of flow. Again, these last three devices read level only, not direction. Now, how are the flow calculations done? Well, when you program your flow meter, you tell it the primary device you have, if it's a Palmer bolus or partial flume, and then we use a secondary device, as I mentioned, which would be the flow meters or data loggers and the level. And what it does, when you tell it that you have a partial flume, it goes to a lookup table, looks at the head height, and then gives you the appropriate flow rate. One thing I'm proud to announce that we have re-released the ISCO Flow Calc app. So go to your app store, look up Teledyne ISCO Flow Calc, and download that app for free. It has all these tables and area velocity conversions in that app. I think you'll find that very helpful. And it also has a link so you can request the flow data handbook. So now that we have the flume in place, the secondary devices, how do you get your data? Well, one, you can manually download the data, going out to your meter, plug it in with your laptop, download the data. Modems can be added, so you can automatically have the data sent to you, or you can call it from your office. The other great thing about having a modem on there is now you can use your device to send you an alarm if there's a high flow condition or low flow, whatever it may be, so you can get instant notification if there's an issue going on at your site. Modems also allow for automatic data pushing. So as seen in the screen down below, this is our FlowLink cipher, where you can push the data from your sites directly to cipher and allow you and other people to have complete visibility of your sites to make sure everything is running properly. And last, as far as the other way to get data out, is you can use analog output or Modbus provided on most flow meters to send your data to a SCADA system. So with that, we've given you a lot of information. I'm going to turn this back over to Sharon.
Well, thank you so much, Andrew and Darrell, for sharing this valuable information. We are opening it for questions. You can find on GoToWebinar, there is a questions tab. So please feel free to add questions there. We have received a few questions, so let's get started with those. The first question is addressed to Andrew. Can flumes be freestanding?
Yeah, that's a great question. And the answer is yes and no. Some smaller flumes, so smaller partial flumes, anything under 6 inches, and some Palmer boluses can be freestanding. But for larger flumes, they're designed to be liners, and they need to be set in concrete and completely encapsulated in order to keep their rigidity and strength and your tolerances and your dimensions.
Okay, perfect. Let's see here. We have another question. How do I accurately read flow during a submerge?
Yeah, so the answer is it depends on your flume. So I guess for this example, we use a partial flume. In that case, if you are submerged, there's a ratio that you can look up in the Teledyne ISCO Open Channel Flow Measurement Handbook. It dictates all of those ratios. And with that, you'll need to take two measurements, one at your standard point of measurement known as HA, which is in the converging section of the flume. Then you'll need to take a second in the throat at the 0 point being the elevation of the floor of the flume. Then you compare those, you look at the ratio, and if you're in a certain value range, then you'll need to either do a flow calculation, which is in the book as well, or you'll be fine. So the answer is you just need to take a second point of measurement and do some math, but it is possible.
Thanks, Andrew. I want to add one thing to that. The other option is if you don't have the two sensors on there to read the two different locations for the calculation, you can use an area velocity sensor. And what we found is that if we've had some clients that had common submergence of their flumes, and so what they've done is they've taken our wetted area velocity sensor, put it in the upstream pipe because it will then read the level and the velocity to calculate the flow. So that's just another option for you. But, thanks. Sharon, do you have more questions?
Yes, there are. Here's another question. I'm assuming this is in regards to sensors. What are my options if installing in a manhole?
So it's kind of a two-part answer to that. So as far as if it's a manhole application, you can use an area velocity sensor such as the laser flow sensor or our 350 intrinsic safe area velocity sensor. If it's just an open channel, round pipe, or rectangular channel with an opening, we can slide that in there. But I believe Andrew has some flume options as well.
Yeah, depending on whether or not the manhole is existing or not already, limit your options because some flumes are going to be larger than your standard 48-inch diameter precast concrete manhole. And if they are, you might need to go in and cut out your manhole in order to fit the flume in there. Another option is to get a prefabbed, prepackaged metering manhole that has the flume built into it straight from the factory. And that can be installed a lot quicker if there is an option to do a new manhole.
Okay, Andrew, here's a question for you. What is a submerged condition in a flume?
So submergence is when there's a backflow of water, say the effluent isn't clearing or flowing freely as it needs to, and you're getting some backflow back up into the throat of the flume or the V-notch or whatever the throat is going to be on that. And like I was discussing earlier, if that is the case, you'll need to take a second point of measurement, and that's dictated typically in your shop drawings, and you'll need to do a conversion factor equation in order to figure out your flow. But like I said during my presentation, the best course of action is to design for free flow at all costs. You'll remain more accuracy that way, and it'll just be easier for everyone. You'll save money. You won't need to have two sensors. But submergence, to wrap it up, is when there's a backflow of water going back into the flume rather than draining clearly.
Okay, let's see here. Here's another question. The flow is coming into the flume too fast. Can this be fixed?
Yeah, so when your flow is coming in too fast, chances are you're going to be already at a critical flow rate, which is when your Freud number is higher than 1. And if that's the case, the flume just is not going to operate accurately. That's how flumes work. They move flow from subcritical to critical. So if you're already critical, you're going to need to slow things down upstream. You can do that with baffles or another hydraulic jump of some kind, but it typically needs to be 20 throat diameters upstream of your flume in order to be able to get things back to being laminar, uniformly distributed, and subcritical at that point. So You need to have some sort of jump upstream to slow things down.
Okay, very good. Let's see, Darrell, here's a question for you. What maintenance is required on the level sensors?
That's a great question. So depending on which sensor you have in there, if it's an ultrasonic sensor, there's minimal maintenance required because it is out of the flow stream, but you may find that you have, spider webs or other things, attached to the sensor that you may have to clean off. The other thing would be the flume itself. So if you find that your levels are starting to get higher or your ultrasonic quality is being reduced, chances are you may have some debris in the bottom of that flume that needs to be cleaned out. Now, as far as the other sensors that are in the water, the bubbler and pressure sensors, occasionally you will have to clean out the flume if you have sediment and debris starting to build up on top of that sensor.
All right, and here's another question. What is the minimum grade coming into a flume?
Yeah, that's a great question. It's one I get frequently, and unfortunately, it's not one that there's a good answer to. It kind of boils back to the three words I've been saying over and over again: is that the flow needs to be subcritical, tranquil, and uniformly distributed. So there's not really a good answer on what the grade needs to be. It just needs to be low enough to where your velocity is low enough to where you're going to be subcritical, and in some cases that can be 2%, maybe even 3%, but it boils down to you need to be able to do some modeling and do some other types of research to figure out your flows are going to be slow enough in order to get into the flow that's subcritical.
Okay, here's another great question. Why use a flume over a weir?
Yeah, that's a great question. One right off the bat is sedimentation. If you're going to be in a situation where you have a lot of sediment running through your effluent, a weir is going to fill up quickly, depending on how much sediment in there. You have a lot of sedimentation falling into the bottom. They need to be maintained more often, and they need to be drained and cleaned. Another good reason is the flows. Weirs aren't really good at accurately measuring a very small, low set of flows very accurately. So anything from 4 gallons per minute up to about 219 gallons per minute in a standard Tracom weir box, depending on the V-notch size. So they give you a really clear picture of small flow rates. Flumes are going to give you a much larger range of flows to look at. In some cases, they can be a little bit cheaper too and easier to install in a flow situation. So that's my wrap up there.
Okay, here's another one. Are there temporary flumes?
Yeah, so that kind of goes back to the freestanding question a little bit. We do make a lot of flumes for research applications, so especially out in the Mountain West, different universities and researchers taking small trapezoidal flumes or H flumes up into the mountains to test different headwaters, different tributaries of major rivers. So yeah, you can definitely be temporary. Small flumes are easy to transport and get out there. Like I said earlier, a lot of flumes are public domain. Their dimensions are published, so you could make something out of plywood if you needed to. But yeah, no, we do definitely make temporary flumes. We even make nested flumes, so especially in the world of partial flumes, if you're looking at a situation where you have development that's going to be growing in phases, we'll put a temporary flume inside of a larger flume, and as your development grows over the course of 5-6 years, you can remove that temporary flume from the larger flume, and then you have an expanded flow. That saves money in the long run too, because you're not buying 2 flumes and having to do excavation. It's all in one convenient wrapped up piece.
Okay, we've got a couple more that have rolled in. How do I measure submergence in a partial flume?
Yeah, that's a great question. And we'll pop through that one a little bit there. So with a partial flume, you got to look at the measurement in the throat at your grade elevation, and then your measurement at H sub A, which is in the converging section. And compare those, and depending on which size of flume it is, you'll have to look at the ratios. Let me see if I can pull it up quick here. So for smaller flumes, you're looking at about a 50% ratio, and then it just kind of goes up in increments of 10 to 60, 70, and 80%, depending on the size of the flume. And if you're over that value, you'll have to do the equation, which is a little bit too mouthy to get into in this platform, but it's a publicly available formula. You have to run everything through. And I believe Darrell can comment whether or not the 2 meters can do that automatically as well.
Yeah, our signature meter, we've actually have a ratio equation built into the signature meter, so that is an option where you can add multiple sensors on there. So you could put the 2 ultrasonics on there to read the different levels, and then we have a ratio calculation already built into that. So good point, Andrew.
Okay, let's see here. Here's a last question that's come in. I do not have the full recommended approach for the flume size I need. What are the options?
Yeah, so we see this a lot in maybe an expansion of a treatment plant or a new plant where you just have limited options as far as your property or your easement. And the answer is the full recommended in straight flat into the flume is just a recommendation. If you can get things to be subcritical, uniformly distributed, then you're going to be fine. You can use different things like baffles, like I said earlier, to slow things down, and a few other different design tricks in order to get that length that you're going to need. But at the end of the day, those are just guidelines, and you can kind of finagle it to make it work. Because we understand that you're not going to be able to have unlimited run, especially if you're expanding a plant and things are already existing. We're going to have to make things work, and we can definitely work through things on specific situations to make the flow work accurately.
Okay, great. Well, that looks like all of the questions that have arrived. If any of you do have further questions, you certainly can message us through GoToWebinar, and we would be happy to pass those on to Andrew and Darrell. I want to thank you all for submitting all of the great questions. And if we didn't happen to get to your question, we will send you an email, and we just may need further clarification on what was asked. So with that, I would like to invite you all to follow Teledyne ISCO on social media to keep up with what is happening. I know Tracom also has social media. In fact, I follow them myself on LinkedIn, so you can easily follow them, and it's a great way to stay informed. So thank you again to Andrew and Darrell, and thank you to everyone for joining us, and we hope to see you again on our next airing. Take care.